I think most of the students have joined. We shall continue with this. 110, it is nillium. So for digit 1, it is U. For digit 1, again it is U. And nillium is UUN. So nillium. This is how we can write the names of any element having atom number greater than 100. So this is very simple. So I am giving here one more atom number, that is atom number 111. You have to write the IUPAC name for this and let me know what you have written. Try to write the name of this element. For digit 1, we have to write again un. For digit 1, again we have to write again un. One more digit 1 is there, so again un, and that ends with unium. So we have to write this as a unium. And the symbol is very interesting. U. 111. Unium. This is how we can write this as a unium. Now I shall jump to 115. You have to arrive at the name. I think it is very simple. How can we write? For digit 1, it is again un. For digit 1, again it is un. And for digit 5, it is a pent. And that should end with IUM. So unpentium. Unpentium. UUP. Then 120. How can we write for 120? For digit 1, it is un. For digit 2, it is a by. And for 0, it is a nil. That should end with IUM. So unbinillium. So unbinillium. Now I would like to tell you one interesting point while studying this IUPAC nomenclature is that for atomic number 102, the name is unnilbium, but exact reverse name is there. For atom number 20, it is unbinillium. Here the symbol is UNB, but here the symbol is UBN. So if you make a mistake during the writing of this, then the atom number or the name may change. So this is a drastic feature. Now again 125. It is unbinillium. Unbinillium. UBN. Sorry, UBP. Then 103. Sorry, 130. Here we can write the name as un for digit 1. For 3, it is a tri, and for 0, it is a nil. Nil becomes nillium. So untrinillium, UTN. Again, here, see here, for atom number 103, it is unniltrium, UNT. And for atom number 130, it becomes untrinillium. So again, there is a relevance between the symbols UNT, unniltrium, and here untrinillium, UTN and UNT. Don't make confusion between these two names and their symbols. Then atom number 140. In between the atom numbers, you can easily write. For digit 1, again it is un. For digit 4, it is quad. And for 0, it is a nil, which should end with nillium. So unquadnillium. UQN, which is exactly reverse to that of 104. For 104, it is unnilquadium UNQ, but here unquadnilium UQN. There is a relevance between UNQ and UQN. So don't make confusion between these names and their symbols. And the last member I am giving here 150 is very simple. It is unpentanilium. Unpentanilium. So unpentanilium, UPN, very simple. So this is how we can give the names and the symbols for all these elements. This is how we can arrive at the names of SHE elements with their during this study of this topic. So far we have completed the lanthanide elements and the actinide elements, wherein we have studied the lanthanide electronic configuration, then the oxidation states, the lanthanide contraction, the position. With regard to actinides, we have studied the electronic configuration, then the synthesis of transuranic elements, and just now we have finished the nomenclature of IUPAC nomenclature of SHE elements having atom number greater than 100. So this is how we have completed. Very important topic from your examination point of view is chemistry of F block elements. We shall proceed further with the next topic, which is also very important, because the two topics that I am going to discuss here, those topics are very important from the examination point of view, because these are the two topics they carry maximum weightage during your exam time, and hence I am taking this topic after the completion of F block elements, which is again equally important from the examination point of view. It is a nuclear chemistry, which is also very interesting to study. Now, while studying this topic, nuclear chemistry, we have to study this topic with the help of certain nuclear reactions. We have to study what is the exact definition of nuclear reactions. We are going to study the energetics of nuclear reactions. Then we are going to study the classification of the types of nuclear reactions, where we are going to study 5 different types of nuclear reactions, because this particular topic that I am going to deal with today contains so many nuclear reactions, and if we understand those nuclear reactions which we have already studied during the actinide elements, then the topic is very simple to understand, because so many nuclear reactions are there. So whenever there is a question of nuclear reaction comes, one should be very careful during the balancing of all these nuclear reactions. In this topic, we are also going to study very important aspect of this topic, that is nuclear fission and nuclear fusion reactions. Perhaps you might have studied these reactions at your 12th standard. So a little bit detailed study is expected at this level. After completion of these nuclear reactions, that is nuclear fission and nuclear fusion reactions, we are going to study the use of uranium, thorium, and plutonium in atomic energy, and lot of studies were going on worldwide, and the uses of these radioactive elements, because all the actinide elements are radioactive in nature, and hence the study of which is very important, and scientists were put forward certain fruitful results with regard to the applications of all these elements, because perhaps you might have heard that nowadays radioactive cobalt is used in the treatment of cancer. Certain crops where the fungal attack or some certain insects which attack on food giving plants, those insects can be cured by using certain radioactive spraying agents, which can minimize the loss of these food giving plants. So carbon is also used during certain cases. So certain applications, those where we are going to study in this nuclear chemistry. So the topic, as I have told you, is very interesting to study, provided you listen very carefully and attentively. Now, while studying this topic, as we know that one should know what is a nuclear reaction. We have studied so many nuclear reactions in the beginning of attending a topic, where a target nuclide is there or target nucleus is there, with which a projectile is bombarded and particles are ejected. The product nucleus is obtained and particles are ejected. The product nucleus thus obtained is also known as a recoil nucleus or daughter element or daughter nuclei with the ejection of certain particles. These particles may be protons 1h1 or gamma particles, which are chargeless and massless particles, or alpha particles helium-24. These particles are ejected during the course of these nuclear reactions. So nuclear reaction can be defined as the reaction in which the atomic nucleus is transformed or the atomic nucleus is transmuted into some new product or some new element, or in other words, nuclear reactions can be defined as the nuclear reactions which yield the new element having composition which is entirely different from its parent nucleus or from its the target nucleus. So after transformation or transmutation by using certain projectiles, the new nuclide or daughter element thus produced is having certain different composition. Let us study how these nuclear reactions are to be studied and how the nuclear reactions are to be balanced and what is the energetics of these nuclear reactions. Just see these nuclear reactions. Just now I have mentioned that a reaction in which the atomic nucleus undergoes transmutation or transformation is called a nuclear reaction. In other words, we have seen that the nuclear reactions are those in which the nuclear composition is changed. The nuclear composition is changed means the number of protons, the number of neutrons, all these are changed. That is, there is a drastic change in the composition of the nucleus. For example, if we take an example of, this is the name of the topic, that is nuclear chemistry, which is again included under paper number 13 in organic chemistry. Here, if we take for instance the example of aluminum, atom number 13, atomic mass is 27. Here, if aluminum is bombarded with deuterium, hydrogen 1h2 deuterium, here, first of all, I would like to make you familiar with this deuterium. As we know, there are three isotopes of hydrogen. These are the three isotopes of hydrogen: 1h1, 1h2, and 1h3. Here, this first species is known as a proton, which is denoted by a letter small p. Here, this is known as deuterium, which is abbreviated as D. And here, this is known as a tritium, which is denoted by letter T. So during the notations, when we give for these projectiles a letter P, D, or T may be used. So whenever we use a letter P, that stands for a proton. For D, it is a deuterium or deuteron, and for T, it is a tritium. Certain gamma particles are there. These are known as gamma particles, and alpha particles are there, which is nothing but a helium nucleus. So we shall come across either of these ejectiles during the course of these nuclear reactions. Now here, in this course, if one neutron is ejected, I think you might remember, if we know the number of neutrons which are ejected or the ejectile, if it is a neutron, the remaining product here 13 plus 1 is 14 and 27 plus 2 is 29 minus 1 is 28. Atom number 14 is of silicon. So here this is a target nucleus, as we know, we have studied this. This is a projectile or bombarding agent. This is a product nucleus, or which is also known as a recoil nucleus, or it is also known as a daughter element, and this is a ejectile. This is known as a ejectile or particle that is ejected. Now, one point here noted that while carrying out such nuclear reaction, we have to balance the mass number. At the top, we write the mass number, and at the subscript, we write normally the atomic number. So, whatever the mass number and the atomic number, this is known as a superscript, and this is known as a subscript. So, if atom X is there, the mass number is at the top, that is a superscript, and atom number at the subscript. Here, whatever number of mass number and atomic number must equal to the number of atoms which are present on left hand side and on right hand side. Then and then such nuclear reaction is known as a balanced nuclear reaction. A balanced nuclear reaction. What is a balanced nuclear reaction? A nuclear reaction where the number of mass number and the atomic numbers on both the sides of a reaction, that is on left hand side, that is the reactants, and right hand side, that is the products, those should be balanced. Just now I have balanced here all the atom masses and atomic numbers for this nuclear reaction. Such a nuclear reaction is known as a balanced nuclear reaction. Now, in a modern terminology, it is not at all necessary to write such a lengthy nuclear reaction. This same nuclear reaction can be written in some different form. How can we write? First of all, we have to write a target nucleus, followed by the product nucleus. First, we have to write a target nucleus. Then, at last, we have to write a product nucleus. In between these two, a projectile and the ejectile are written with a comma sign. So, P stands for a projectile, E stands for ejectile. So, by using this rule, how can we write this particular nuclear reaction? Here, target nucleus in this case is aluminum. So, aluminum 1327. Then, the product nucleus is here, silicon 1428. So, silicon 1428. So, at first we have written the target nucleus, at last we have written the product nucleus. In between these two, we have to write first of all the projectile, which is a deuteron, and the particle ejected is a neutron, for which we can use this letter small n. So this is how we can write this particular reaction. This is known as a balanced nuclear reaction, and this notation is known as the Bethes notation. So according to Bethes notation, we can write this particular reaction, that is a balanced nuclear reaction, in this format. So according to modern terminology, this reaction is also known as the DN reaction or DN process. What is the DN process? Where a deuteron is used with the ejection of neutron, and hence this process is known as the DN process. Now, what is the energy terms, or what is the energetics of these nuclear reactions? Now, when these nuclear reactions proceed, the reactions, they are accompanied by either gain or huge amount of loss of energy. If in a particular nuclear reaction, if there is a gain in energy, such nuclear reaction is known as endothermic reaction, or what we know as a endothermic reaction. So when a particular reaction, nuclear reaction, when to proceed further this reaction, certain amount of energy is to be supplied. So by gain of energy, when a particular reaction proceeds, it is known as an endoergic reaction or endothermic reaction. In other words, when during a nuclear reaction, when the lot of heat energy is evolved, it is known as an exoergic or what we call as a exothermic reaction. These terminologies we know very well. So whatever the energy that is evolved, this energy that is denoted by a letter Q. So you should remember this letter Q that is given for either gain or loss of energy. Now, whenever there is a endoergic reaction or gain in energy, we have to assign whatever energy is there a negative sign. Or if there is a loss of energy or exothermic reaction, we have to assign a positive sign for such a nuclear reaction. So in brief, the quantity Q may be either positive or negative. So this quantity Q may be sometimes positive or it may be sometimes negative. So when where this positive or negative sign or positive or negative Q signifies the release of energy that stems from the endoergic or exoergic reaction. So if we designate energy by Q is equal to positive, this is an exothermic reaction. Or when we write Q value as a negative, it is an endoergic reaction where a gain in energy takes place. I would like to give you certain examples. Here, whatever energy that is evolved, a huge amount of energy is evolved during the nuclear reactions, and this is a very important criterion for nowadays mankind, because whatever energy that is released during nuclear reaction, this energy is utilized in the production of electricity in most of the foreign countries, not in India, because in India, the hydroelectric power stations from which the electricity is generated, but in foreign countries, they have to rely upon the nuclear plants for the generation of electricity. So whatever energy that is involved, that can be calculated by using Einstein's equation, which is E is equal to mc square, where here E is nothing but this is a total energy, then M is a mass defect, and C is a velocity. C is a velocity of light, which is a fixed value 2.998 into 10 raised to 8 per second. So this is how we, if we put these values, we can calculate whatever amount of energy that is released, but the calculation is not expected at your level. Just I am giving how the energy that is released, huge amount of energy that is released during these nuclear reactions from the equation of Einstein's equation that is calculated. Now, I would like to give you one example of the endoergic and exoergic reaction. For example, just now we have seen that certain nuclear reactions, those proceed with a gain of energy. For example, here take for instance the example of nitrogen 714 with alpha particles such as helium-2 In this case, if a proton is ejected, what is remaining? It is very simple. 7 plus 2 is 9, minus 1 is 8. 4 plus 4, 18, minus 1 is 17. Atom number 8 is of oxygen. Here, this particular nuclear reaction is accompanied by a gain in energy, that is 1.16 milli electron volts. So here, this is how we can calculate the reaction, the energy of this reaction. This reaction is known as endoergic reaction because the value of Q is negative. Here the value of Q is negative. So this is a nuclear reaction. Another example I would like to give you for the exoergic reaction. Take for instance the example of lithium, atom number 3, atom mass 7 with protons, that is 1H1. If we carry out this particular reaction, during this case, if 2 alpha particles are ejected here, 3 plus 1 is 4 and 7 plus 1 is 8, 4 multiplied by 2 is 8. Here the value of Q is positive, it is about 17.25 milli electron volt. Or one simple example that I would like to give you here for this. Here, suppose for example, if 2 deuteriums are there, 1H2, here during this process, if 1 proton is ejected and here the value is 4.0 milli electron volt, what is remaining here? 1 plus 1 is 2 minus 1 is 1. 2 plus 2 is 4 minus 1 is 3. So a tritium is formed. So 1H3 is a tritium, just now we have discussed. So this is again a exoergic reaction. Now, during this nuclear reactions, certain energy that is evolved that we have calculated by using this Einstein's equation, because of which it is very easy to calculate whatever amount of that is released during the course of these nuclear reactions. So this is how the energetics of nuclear reactions that we have studied. So in brief, if we want to conclude these energetics of reaction, that in all these reactions, here it is again showing I am running out of time, only few minutes are left, so I have to conclude within 5 to 6 minutes. Now these reactions are accompanied by either gain or release of energy. If it is a gain in energy is there, we have to assign a negative sign, and if there is a energy that is released, we have to assign a positive sign. Now here I would like to give you certain points of interest amongst these types of nuclear reactions. Under the types of nuclear reactions, again here we are going to study certain nuclear reactions. Just now I have mentioned that there are 5 different types of nuclear reactions. Those are the artificial transmutation or artificial disintegration. Second type is artificial radioactivity or artificial or induced radioactivity. The third type is nothing but the projectile capture reaction. Fourth is projectile capture particle ejector reaction, and fifth is a nuclear reaction. So these are the 5 different types of these nuclear reactions. We shall study all these types one by one by taking into account very simple nuclear reactions. Those are very simple to understand and very easy to remember also during your exam time. The first type is known as the artificial transmutation. Artificial transmutation means the nuclear composition has changed when we carry out such artificial transmutation, or this is also known as a artificial disintegration. You have to remember these 2 words, because during exam time the examiners may twist the question that discuss artificial transmutation or artificial disintegration. So what is this artificial transmutation or artificial disintegration? The conversion of an atom, as we know, of one element into another atom of an element by artificial means, that means by man-made, or it is synthesized artificially, it is known as artificial transmutation or artificial disintegration. In artificial transmutation, certain helium, proton, deuterons or neutrons are used as a projectiles or as a bombarding elements. These projectiles are thrown on the target nucleus with a greater speed and for which the cyclotron or helium instruments are used so as to accelerate the projectiles. If we try to study how the transmutation, there is artificial transmutation that can be carried out, the transmutation that can be carried out by alpha particles. How can be calculated by alpha particles, that we have to study. Alpha particles means, as we know, it is a helium nucleus. So here all such transmutations which are carried out by using alpha particles as projectiles, then such reactions are grouped under the transmutation, that is a artificial transmutation or artificial disintegration. How this artificial disintegration is carried out? Just see here. For instance, we can take for example beryllium-49, with which, as it is a transmutation by only alpha particles, hence we have to use only alpha particles here. During this reaction, if one neutron is ejected, now the reaction is very simple. If we know the number of neutrons which are ejected during this course, here how can we calculate, or how can we arrive at the product nucleus? 4 plus 2 is 6. 9 plus 4 is 13 minus 1 is 12. Atom number 6 is of carbon. Now here, this reaction is also known as the alpha N process. This reaction, that is a nuclear reaction, is known as the alpha N process. Why it is alpha N process? Because the projectiles are alpha particles and these are the ejectiles, that is the neutrons are the ejectiles. Or the same reaction can also be written as beryllium N process. This is known as a beryllium N process. Why it is beryllium N process? Because here, as we know, only alpha particles are used, so not necessary to write here alpha. Only the target nucleus and the particles ejected, those if we write, then it is very easy to carry out this reaction. Another reaction that I would like to give you here of nitrogen 714. Again here, the transmutation by alpha particles, hence there is no choice. We have to use helium nucleus. During this course, if a proton is ejected, now the case is very simple. If proton is ejected, so 7 plus 2 is 9 minus 1 is 8. 14 plus 4 is 18, minus 1 is 17. So an isotope of oxygen is obtained by bombarding this nitrogen nucleus with alpha particles. So how can we write this reaction according to Bethes notation? Here the particles we have used is alpha particles and protons are ejected. So this reaction is known as alpha P process. Alpha P process, or the same reaction can be write as the nitrogen and protons are ejected, hence NP process. Here N stands for the nitrogen, P stands for the protons which are ejected during this course of transmutation. So this is how we have seen how the alpha particles may be used during the transmutation by either of these target nucleus. So while studying the topic nuclear reaction, we have come to the conclusion that every nuclear reaction is to be balanced. The mass numbers on left hand side and the atomic numbers which are present on left hand side must be equal to the mass number and atomic numbers on right hand side. Hence we can write this, we can refer such nuclear reaction as a balanced nuclear reaction. Also, these nuclear reactions are having certain energetics. Some reactions they are accompanied by the loss of energy, or some reactions are accompanied by gain of energy, according to which a positive sign is assigned for exothermic or exoergic reaction, and a negative sign for endoergic or endothermic reactions. So this is how we have come to the conclusion. We shall begin with this topic tomorrow also. That will